Hi guys. So welcome to lecture 3 for Math 350. Today we're going to talk about how expressions are stored internally. So something about the structure of how expressions are stored, and then how we can manipulate that, which is called changing heads in Mathematica, which is essentially switching data from one type to another, and you can actually perform operations that way because of the way that Mathematica stores its data internally. Let's start by talking about expressions. So if we consider the following expressions, say a plus b plus c, and you execute that, of course Mathematica is going to spit out the calculation a plus b plus c because it's a symbolic calculation. But you could do the same thing where if you had 2 plus 3 plus 5, it's going to get you 10, right? So 2, 3, 5 together, you chain them together with plus, you get 10. The same thing with a set notation or a list. So ABC is a list in this case, but you can do the same thing where you take the numbers 2 and 3 and 5 and you assert them as a list and you get a list. Same data, the 2, the 3, and 5 are the same data, but what they're contained in is different. And then finally, the way that Mathematica encodes multiplication is with spaces. So Mathematica is by default is going to interpret a space as a multiplication. You can see that because there'll be a ghost multiplication sign when you write something like 2, 3, 5 with spaces in between, and that evaluates to 30 in the same way that the symbols A, B, and C evaluate to ABC. If you actually look at how these things are structured, though, they're very similar in their structure. The ABC is being manipulated in 3 different ways, but the A, the B, and the C themselves are the same. So you can use a command called full form, which will show you exactly what a computation or a composition of functions is doing. So if you apply the full form command to a plus b plus c, you can see that it's wrapping the a, b, and c inside of an object called plus. And the plus that's up at top of that is called the head of the object. Now, if you ask it to give you the full form of 2 plus 3 plus 5, it's actually going to do the computation first and then tell you the full form of the answer. So that's not as illustrative. And that's why we're using symbolics for the calculation here. Because again, if I ask it for the full form of 2 plus 3 plus 5, it's not going to tell us that that's in a plus environment. But if I construct the same exact object, plus 2, 3, 5, then the plus 2, 3, 5 is a way of taking the objects 2, 3, and 5 and applying the plus structure to them. So what is the full form of ABC in a list? Well, it's the list object. And you can construct that 2, 3, 5 list in the same exact way. You could list 2, 3, and 5, and it will put 2, 3, and 5 into a list object. The full form of ABC multiplied is times ABC. And again, with the numerics, we can't do a full form of 2 times 3 times 5 because it will evaluate it first, but we can show that it's doing the same thing by writing down times 2, 3, 5. Now that might seem like an artificial way of encoding these things because I could just write 2 times 3 times 5. Why do we need to surround it with this times head and embed it in an object that's doing multiplication? Well, one of the fanciest things that Mathematica can do is flip the heads that are attached to a particular object. So the plus, the list, and the times is called the head. You can always see what the head of an object is by, if you don't want the full form, because full form can get pretty crazy. So if you did something like the full form, say, of A, B, C, A, B, then that could be really hard to interpret because it's telling you how every single object in this is embedded in every other object and what the heads of all the sub-objects are as well. What we really care about when we're doing these computations usually is what the head of the big object is. So you can always compute that by using the command head. So if I was to do the same exact computation on what I just did, but I ask it for just the head of that object, it tells me that it's a list. Okay. So the power of Mathematica is the fact that these can be changed. And that's frequently going to be the case, something that we want to do if we construct an object and with a function and we get a list, but then we want to take that list and do something with it. We want to add it all together, or we want to multiply all the terms together. That typically comes from evaluation, say in sequences and series. So we're going to look at a command called apply, which will let us take one head and replace it for another. So if we consider the command apply plus ABC, or if you like, similarly, we could say apply plus to the list 2, 3, 5. So what is that actually doing? Well, the object 2, 3, 5 here, this object, remember that 2, 3, 5 is a list. So what I'm doing here with a // remember, is I'm applying a function to the previous output. We're going to talk more about this later in the lecture, but it's a good way of applying a function that you've constructed as an afterthought. So I wrote down the list 2, 3, 5. I want to know what kind of object it is. So if I // head, it will just produce that without the need to impose brackets. So what I've done here, what the apply function has done, is it's taken off the head of the list 2, 3, 5 and has replaced it with plus. We can see this much more directly if we work in symbols. Here's another example of the apply function. So if we applied times to say A, B, C, well, then I've just applied times to itself. So maybe if I applied plus to ABC. Okay, that's more what I was looking for. So if you start with ABC, which is a times type object, and you apply the plus head to that object, then you've switched out the sum for a multiplication. And that's really powerful because the sum and product functions require that you operate over an index set. So times is the head of a list that multiplies all the pieces together, but product is like a pi notation where you have to have some sort of formula for the term that you're multiplying together, and then an index that generates the list. So that's another way of doing things, but with times and plus, you can work directly on lists without having to go through generating formulas. And that turns out to be incredibly convenient in a lot of cases. The shorthand for the apply function is just @@, and that's the third of the big categories of symbols, the shorthand symbols that we should remember. So right now we have /@, which is map. We have // which is evaluate the output on a new function. And we have @@, which is the apply function. So if we times on the list ABC, then we've switched the head. So what this does, this switches list for times. And this switches list for plus. So I should point out that sometimes we actually might want to apply a head change on the second layer or the second level of a list. So if you have a list of lists, suppose that you had a bunch of points, 2, 3, 3, 5, 7, 6. And you wanted that list not to be added up all together, but to have each of those sublists added instead. So let's take a look at what would happen if we applied plus to this. If we apply plus to the list as a whole, what it does is it adds things coordinate-wise. So it has added all of the first entries together and then all of the second entries together. That's actually a very useful property. So it's preserved the internal structure of the X and Y coordinates here. But maybe instead what we want to do is we want to add the 2 and the 3 together, and the 3 and the 5 together, and the 7 and the 6 together, which means what I want to do is I want that plus to be applied not to the big list on the outside, but I want that plus to be on the inside. Here's what I'm actually saying. So I'm going to write it out in longhand, and then I'll show you a shorthand notation for this. What I'm actually saying is that what I would like to do is plus at 2, 3, plus at 3, 5, plus at 7, 6. But you can imagine that that's kind of a pain if you have a list of unknown length and you have to go through and actually put the plus in every single entry. That doesn't seem to make a lot of sense. So there are a couple ways to go here. The first is you could map the apply function into the list, but there's a shorthand for that, which is plus @. Take this list right here. And what that does is it maps the plus head change into the list, and then it does the head changing on the first level. So the @@ is an application of a head change, not on the whole list, but on the sublists that are inside of it. Okay. And we're going to need to use both of these when we're generating the solutions to some of the questions in the homework exercises here. Okay, so let's do some examples of using these things, because it's easy to see why we want them if I give you some problems to work on. So let's start by computing the problem, compute the sum of the reciprocals, say, of the first 10 factorials. So I'm just going to build this up from a list. So if I want the first 10 factorials, I start with range 10, which just gives me the list of numbers from 1 to 10. Now factorial, like every arithmetic operation, is listable. So factorial is listable, which means that if you apply it to a list, it evaluates entry-wise. And that's what this is. Now, dividing by a number is listable, or division is. So since division is listable, 1 divided by the range of 10 factorial takes the numbers from 1 to 10, factorials them all, and then takes the reciprocals, which is what we get here. Now, if I want to sum those up, I could come up with a formula for doing this, or I could just take this list and switch it from a list into a plus type object. But I can't use sum, which might seem the obvious thing. Well, okay, let's just put the vector in and sum it up. But the problem is sum requires an index. So instead what I'm going to do is I'll use plus. Now, the naive thing to do would be to apply plus to the list. The problem is, because of the way that Mathematica parses the order of operations, the way that this is being interpreted is it's taking the plus and applying it to the 1. And then it takes that thing and divides it by this list, which is the range of 10 factorial. So the reason why you get the list back again is because plus here is only being applied to the 1. There's a couple of ways to disambiguate this. The first would be to just use the command apply. So if you apply plus to 1 divided by the range of 10 factorial, then you're going to get the answer that you want, because now it's clear that this list is what we want to apply the plus head to. The other way you can do it, which is more common when using shorthand notation, is just to put parentheses around the object that you want to flip the head of, so that Mathematica knows unambiguously what it is that you're trying to do. So that's sort of a baby introduction to how the apply function works and what head switching is. And now we're going to look at a couple of real problems from mathematical history to get a feel for how you can, or when you should be thinking about switching heads, and how it can guide your thinking when you're approaching a problem. So as a good example of how we can use this tool on a problem that's long studied, in fact, probably 4,000-year-old object of interest here, we're going to look at the perfect numbers. So you may already know that a perfect number is a number that is equal to the sum of its own proper divisors. So 6 is a perfect number because the proper divisors of 6 are 1, 2, and 3, and 1 times 2 times 3 is equal to 6. Okay. So we're going to ask Mathematica to find more of them. Now we have a command divisors that will give us all of the divisors of 6, but the problem is I don't want the 6 in there. And the easiest way to get the 6 out of the picture is to use a list manipulation command called most. And you should be familiar with these. So what most does is it drops the last term of a list. And actually it's got a partner called rest, which drops the first term and gives you the rest of the list. So with no parameters added, what most does is it just gives you everything in the list except the last term. And that's exactly what we need if we want to study perfect numbers. So if we most the divisors of 6, then we drop the 6 from the list. Well, that's great, because now I have a list of things that I want to add. So the easiest way to do that, again, because there's no defining formula for how to produce the divisors, I'd really just like to take the output of the divisor function and add it. So the last thing I could do is I could apply the plus head to the list that came out of the divisors. So if we look at actually what's happening here in this command, we're taking the divisors of 6, And then we're taking most of those, which means we drop the 6 from the end. And then this object is a list. So we switch the list from a list into a plus object with the apply command. Or, I think more clearly, we replace the list with a plus object with the double @ command. And that gives us the 6 that we're after. Maybe we could turn this into a function that we could use in a select type construction so that we could find more perfect numbers if we wanted to. So here's an anonymous function that will add up the proper divisors of a number. We know that's the proper divisors because we've mosted the number itself off of the list. So if we evaluate this at 6, we get 6. If we evaluate it at 10, we get 8. Why? Because 1 plus 2 plus 5 is equal to the divisors of 10 without 10 itself. Okay? So now I want to turn this into a Boolean function to check for perfect numbers by checking to see if a number is equal to the sum of its proper divisors. So that's exactly what this function does. I can take the plus, I apply it to the list of divisors without the number itself, and then I check a comparison against the input number itself to see if the number is perfect. And maybe we can check at 6 and see. So if I check this at 6, I get true. I happen to know that 28 is also a perfect number, and it's also true. But we should check it at some other numbers as well, just to make sure that our function acts like we think it's acting. So what I'm going to do is I'm going to map my anonymous function onto a list of numbers. Maybe, I don't know, 6, 7, 8, 27, and 28. So I know 6 is perfect, that spits true. 7 and 8 are not perfect, and neither is 27, so I get false, false, false. And 28 is a perfect number, so I get true again. And so this object right here, this is the perfect number finder. So now I can just use it as the Boolean condition inside a select function to find the rest of the perfect numbers, say between 1 and 10,000. So if you run that command, you get 6, 28, 496, and 8,128 are the perfect numbers between 1 and 10,000. And I think that even the ancient Egyptians knew that 6, 28, and 496 were perfect. This turns out to be a significantly more complicated problem when you have to find all the divisors, and particularly when you're working in number systems that don't have places. So the Egyptian number system did not lend itself to like exploration of the divisors of larger numbers. Now we could check and see that we believe this by finding the divisors of 8,128. And then I guess we should take most of those. So we get the 8128 out of the picture. And then we should add them up to make sure that we get 8218 back out again. So if I apply plus to that list, I get... Wow. Well, that's not a perfect number, but I bet this is. Yay, okay, I did it correctly. Yeah, so you get an unexpected result. Make sure you double check to make sure that you didn't make a mistake, because the computer is unlikely to have. Okay, so that's sort of our first exploration of, I think, a very straightforward application of why you'd want to do head switching in the context of a very well-studied type of number theory. So now I want to consider a slightly more complicated problem. So we're going to look at an object called the practical numbers. So a positive integer is called practical if every smaller integer can be formed as a sum of the divisors of that number. So we're going to try to find all the practical numbers less than 100. And we're going to start like when the perfect numbers with an example. So 8 is an easy number to see as a practical number because the divisors of 8 are 1, 2, 4, and 8. And we don't need to consider the 8 itself because we're looking to build all the integers less than 8. So as before, we don't need the 8 in our considerations here. If I want to know all the possible ways that I can add the divisors together, that's the big question. How do I add all the possible ways that these divisors can be added together? One thing I could do is I could build all the possible combinations of the divisors using an object called the power set. So before I go into the explanation for this particular case, let's look at the list ABC. Remember that the power set of a set is the set of all possible subsets that can be made from that element. So you can get the power set of a set in Mathematica by using the command called subsets. So if you subsets ABC, it will produce every possible subset of ABC that can be made from the elements A, B, and C. So it's the power set. Okay, and here's where we're going to want to use apply on the first level, because if I want to know all the possible ways that I can add the divisors of a number together, I don't want to add this list together because it's not going to tell me anything meaningful. Instead, I actually want to apply the plus environment to everything inside that list. So if I apply subsets to the divisors of 8, you'll see that I get every possible combination of the divisors of 8, not added together, but just as subsets. And then I notice here that I don't really need the 8 because the condition for a number to be practical is that every smaller integer can be made from the divisors of that number. So really I can make this problem run faster if I use the most command in between. So that is all the possible combinations of the proper divisors of 8. Now I'd like to find the sums of these sublists, which is called acting at level 1, which means I want to push the head changing command apply into the list and then apply it to the little sublists. And I can do that with the command plus at, because what that's going to do is it's going to take the plus command and it's going to push it inside so that we get the sum of this set, which is 0, the sum of this set, which is 1, the sum of this set, which is 2, the sum of this set, which is 4, the sum of this set, which is 3, the sum of this set, which is 5, and so on. And you'll notice this is out of order because it's going down our list of subsets in the same order that they were generated here. So when I do the sums, I get 1, 2, 4, 3, 5, 6, 7. And 0, of course, because the sum of the empty set is nothing. So I can organize that list into a set by applying the union command to it. And in that case, let's actually do this. We'll put most on here again. Why make our lives hard? If we apply the command union after we generate this list, then what we're doing is we're taking this and we're turning it into an organized list that starts at 0 and ends at 7 and also drops anything that repeats. That organization is going to be very useful if we're trying to step through a list element by element to see if a certain set of objects is inside that list. So as before, I'm applying union here as a piped command, which means that as an afterthought, I created the list and thought, oh, I should organize it into a list and take out the repetition. Now, the only problem with this list that we've produced is that, of course, we had the empty set in the original list, and that put a 0 into our list of possible sums. But 0 is actually not a possible sum of the divisors of a number. We don't allow that because 0 doesn't divide anything, right? So since 0 is not a divisor, we don't include it in the list. It's an artifact of the fact that we use the subset command to create our list. So we should probably drop the 0, and we can do that by using the rest command. Remember that what rest does is it cuts off the first element of a list and puts the rest of it in. In fact, maybe it would be more natural, since we're talking about piping, generate the list like this, notice there's a 0 in the list that we don't want, and then go back up here and pipe the rest command onto it to drop the 0. Okay, so that's another thing we haven't really talked about yet, but it's possible to chain these piped outputs into each other. So what am I doing with this structure? This creates the list of possible sums and then assigns it to the variable name possible sums. This takes that list before the assignation and arranges it from smallest to largest and drops any repetition. And then the rest command cuts the 0 off the front because it takes off the first element and leaves the rest of the elements. So now the last thing we need to do, if I want something that could find the practical numbers on a large scale, would be to check to make sure that our list of possible sums is actually contained in the numbers less than or equal to our original list. And so for that, we can use a command called contains all. So contains all is a subset checker. So this is a Boolean subset checker. So contains all is a subset checker. So it's a Boolean function that tells you whether or not you have containment in a subset or not. We could say to ourselves, is it the case that the set 1, 2, 3 contains the set 1, 2? And the answer is true, because 1, 2 is a subset of 1, 2, 3. And so for our problem, since we're checking these practical numbers, we started with the number 8. We want to make sure that the integer is less than 8. So we can create that by doing the range of 8 minus 1 for the numbers from 1 up to 1 less than our number. And we want to make sure that that set right there is contained inside. We want this to be a subset of our possible sums. And it's true because our possible sums are the list 1 to 7. So the exercise that I'm going to put on the homework is going to be to find all the practical numbers from 1 to 100. So the last thing I want to talk about in more detail is this idea of piping. It's a constant concern of coding that we want to be able to read what it is that we're doing, and then we also want to be able to debug it. It's very common to not get it right on the first try, or to be building up a line step by step. And if something goes wrong, you want to be able to identify where the error happened. And so piping output is a way of doing that. So a typical sort of pipe would be you start with an input, you apply a function to it like sine 2, and then you realize after the fact, oh, I didn't actually want the sine of 2, which is the completely accurate way of writing that. I wanted the numerical version of the sine of 2. And so instead of typing in the n on the front with the brackets around the outside, you can just / n and get your answer. I use this all the time with matrices. So with a matrix, if you type in something like 3, 2, 1, 3, and you ask Mathematica to present it, you're just going to get a list of lists. So if you want Mathematica to show that as a matrix, which is much easier to understand in these big computations, then you can ask it to, say, row reduce that matrix, and then to put that matrix into matrix form. So that's what this set of commands does. It starts with the matrix that we started with, I guess with an additional row, and then it row reduces that. But that produces another list of lists. So it's not clear what we started with and where we ended as a matrix. And so if I want that to be in matrix form, I can apply this command. But it's actually sort of harder to read stacked up like this. It's easier to write the array and then row reduce it and then put it in matrix form. So just like / n is really common for putting things into numerical form, it's very, very common in linear algebra contexts to be applying matrix form to the output of some complicated computation. Another way you might see this would be if you generated a table. Tables are lists of lists. But if you would like it to be presented in the form of a table, which is easier to read visually, you can apply table form after the fact to get a table. So the last thing we'll talk about is how we can pull apart complicated nested functions into easier to understand pieces. So here's what most people's answer to exercise 3.3 looks like. You've got this function a, which is equal to m plus 3 cubed plus 1 over 3m. We want to find all the numbers between 1 and 500 for which that function spits out an integer. And so if you do it without the length, so you erase the brackets here, and this tells you what they are. And what most people did when they wanted to find the length was you surround this with a length command, and that will tell you that there's 2 elements in that list. And then if you want to know if they're all odd, then you can stick the function odd q on the outside, and it will apply the odd q Boolean check to the elements of that list, and it will tell you that they were both odd. Okay, so there's an argument to be made here that this is cleaner and easier to read if you do it in a piped form instead. So what do I mean by that? Well, if I want to know how many of them there are, what I can do is create that table of all of the possible outputs of that formula for input values from 1 to 500. And then once I have that table, feed it into this function as the input that selects out those that are integers. And then once I have that, then I can compute the length of that list by piping that output into the length function. And if I want to take that same thing and apply odd to it, I can just switch out the length with odd q instead. There's an argument to be made that this is easier to read, and it's definitely easier to debug and to modify because I can just flip these functions without having to make sure the brackets are balanced or add brackets. I have a single output that I'm feeding into a new function that takes a single input. I can just append it to the list by piping the output into another function. So you'll see that in some of my solutions and examples. In fact, in this lesson, I've done that a couple of times already. So for readability and for debugging purposes, when you have the opportunity to do this and to increase clarity, I recommend that you do. Okay. All right, so this is enough to get you guys started on the homework. There'll be another lesson this week following up on anonymous functions, and then we're going to introduce maybe a mathematical area where these things apply to. I haven't decided exactly what area yet, but we're going to be working, since we've been working on number theory, I think it would be interesting to work on these combination of integer type questions, which have a very long history in mathematics and that are at the basis of kind of number theory and some ideas in combinatorics. So this is our first place where we can actually do some real mathematics, and there'll be some exercises on the homework that indicate some of these classic problems. So get started, and I'll see you in the Slack channel. Take care.